here, they are visible from some point in UV. Okay. So it is like this. Suppose I want to.
Not ambient light. Okay. Suppose you walk from UV.
Correct.
All the points that you can see at some point or other. That's the one.
So if I want to guard this whole polygon, and I want to walk only on along this wall, then I can see the whole polygon eventually. Yeah. So it's weakly visible from UV. Okay, and a polygon is orthogonal if all edges of the polygon are axis parallel. So, given any polygon, that means the coordinates of the vertices are given and the order of the the boundary order is given of the vertices. So, this cycle, we can compute its visibility graph in polynomial time. Yes, everything like this we can do, that is okay. But now suppose we are given a graph, just the graph. Question is, does there exist a polygon for which the given graph is the visibility graph of the polygon? Yes. So this is called the recognition problem. That means, given a graph, we will have to say whether it is a visibility graph of some polygon or not. We have to recognize it as a visibility graph. Yes. And related problems are identifying the set of properties satisfied by all visibility graphs. That is called the characterization problem, and the problem of actually drawing one such polygon whose visibility graph is the given graph G is called the visibility graph reconstruction problem. So essentially, if we can solve the reconstruction problem, we can also solve the recognition problem. But it turns out that recognition itself, just saying yes or no, is extremely hard. And okay. So Everett showed that the recognition problem is in P space. Ghosh in 88 and 97 gave 4 necessary conditions for recognizing the polygon visibility graphs, and Abelo et al., Everett and Cornell and Strinu in different years showed that these conditions are not sufficient. Okay. For some special simpler families, so this I will draw here. Yes.
To find them out,
Polynomial time. Yes. Yes. So there are some very simple kind of polygons. So this on a base UV, if you have 2 concave chains, this is called a tower polygon or funnel. Then you can have this kind of thing, a staircase, and this is called a staircase. Yeah, this is called a staircase. And then you can have 1 convex and 1 concave chain. Yes, this is called a spiral. So for these kinds of polygons, the recognition problem can be solved in polynomial time, because their structure is very nice. Basically, we can divide into 2 chains which have very nice properties. Okay. So this part is known. Also, Lin and Schiena, they showed So, if we want to solve this in polynomial time for general polygons, we would like the coordinates of the polygons to be somewhat nice, yes, but Leninsky assured that sometimes the polygon visibility graphs might require exponentially large coordinates. So, if you are given n vertices of a graph and the edges can be problematic, and the polygon that corresponds to that graph might have very bad coordinates. Okay. Yeah, Leninsky also showed that dominating set vertex cover and NP complete for polygon visibility graphs. They also showed that the graph isomorphism problem on visibility graphs is GI complete. Okay. GI means graph or isomorphism. It's as difficult as the general graph isomorphism problem. Okay. Okay. So, existential theory of the reals denoted by ETR is a complexity class defined by the following complete problem. Given Boolean combination of polynomial inequalities and equalities, decide if there is an assignment of real values to the variables such that the system is satisfied. So, basically a formula like this. So, there exists x1, right, thank you. Okay. So, there exists x1 dot dot xn, then there is a predicate in first order logic. So, this contains plus minus multiplication division, zeros, ones, equality, inequality, etc. Yeah, this is how the formula is written, and if some values of the xi's satisfy, I mean we want to decide if there are x1 up to xn which have real values satisfying this formula. Okay. So, the class ETR, yeah, sorry, of course you have and or, because this is a Boolean combination of polynomial inequalities, right? Yep. Yep. So, this is the class ETR. It is known to be somewhere in between NP and P space, and Hoffman and Merckx have shown that the recognition problem for visibility graphs of polygons with holes is ETR complete. So, actually the earlier result that they showed the problem is in P space. Yeah. So, the way they showed that it is in P space, actually the proof stands for the problem being in existentials itself. Okay. They showed that it can be, the problem can be written down like that. Okay. Right. So, the recognition problem for visibility graphs of simple polygons, that is polygons without holes, that is still open. Okay. It is inside ETR, but its hardness is not known. Okay, this is the first part.
Typically, what are the approaches people take to do this recognition problem?
So, for those simple families, you will look for two chains. Yeah, if you want to recognize it as any of those spiral staircase. So, two chains, how many, like n square possibilities, right? Because you have the outer boundary given to you. Then for each chain you will look for this staircase structure or spiral or concave. So, that is polynomial. Okay. Okay, art gallery problems. An art gallery can be viewed as a polygon with or without holes with a total of n vertices and guards as points in P. Okay, and so let me, yep. So, during a conference at Stanford in 1976, Victor Klee asked the following question: how many guards are always sufficient to guard any polygon with n vertices? Okay. And so, it can be shown that a simple polygon of n vertices needs at most floor of n by 3 guards, and there are polygons that require floor of n by 3 guards. For example, this, for each spike you need a separate guard, so that makes it at least n by 3. For orthogonal polygons, this bound goes to n by 4, yes, because now each spike will be basically rectangular. So, I am going to coloring now. I am not yet there. Okay, so this is something short. Okay. N by 3 is guarding. Yeah, so that is okay. Okay. So, that sometimes n by 3 are necessary is clear from this, right, this comb polygon, because for each spike you need at least one. Now, yes, now there was also this proof that the other side of the claim, that with floor of n by 3 you can always do it. Yes. So, what is the proof of that? Right.
Because our pronunciation is not so compatible with the French pronunciation, right?
Okay. So, this proof was given by Khatal, right? Fisk. Okay. So, you have this simple polygon, what you do is you simply triangulate it. Yes. So, divide this into triangles. You can triangulate it in any way. Yes. Yeah, anyway.
Because you are proving sufficiency, it has to be anyway.
Yes. So, we will use colors. Okay. So, color 1, color 2, color 3. Yes. So, this is basically the subgraph of the visibility graph, as you can see. These are vertices, and now we will color the vertices of the polygon. So, let this be 1. Our rule is that every triangle should have 3 different colors on 3 vertices. Okay. So, this is 1, this is 2, and here we have 3. This first triangle is colored. Now, we see that we already have a triangle which has exactly 2 vertices colored. Yes. So, the third vertex must have the third color, again the same thing happens. Yes, then 2 3 1 3 1 3 and so on. So, we can cover this totally like this. So, yes. So, at each stage of the coloring there is one triangle whose 2 vertices we have colored and the third one is left, and we use the color that is left on it. So, this means
The other thing is outer planar graph. Yeah. Outer planar graph
right,
is vertical.
right,
Actually, we can say that.
yes, yes, absolutely, yes. Oh, but I think those that comes from this, or no, but that proof comes from this one, right? Or yeah, okay, yeah, but it can be said both ways, yes, yeah. So, 3 colors coloring all n vertices, that means there will be at least one color which gets at most these many guards. Yes. So, we choose that very color, and since like all the triangles are seen by their vertices, for each triangle we will find a vertex of this color that sees that triangle. So, that means the whole class of vertices colored with that color will see the whole polygon. Okay. So, it is n by 3.
So, n by 3 guards are sufficient.
Yes, but instead of using n by 3 guards, we can choose this, we can choose this.
The proof is over.
Yes,
Tell that.
and we can choose this. Yes. So, though n by 3 are sufficient to guard the whole polygon, we can do it with 3 guards here. Yeah. So, this is the minimization version of the art gallery problem. We want to know the minimum number of guards that are needed to guard the whole polygon, and this is known to be NP hard. Yes. Yes. Not only NP hard. So, here we are using the vertices as guards. For that version, the problem is NP complete, but if we are allowed to use any point in the polygon, then it has been any internal point. Vertices internal, there is no restriction. Okay. For this case, it has been shown to be ETR complete again. Okay.
What is ETR complete?
Existential theory of the reals, what I talked about just now. Okay. So, it's a class that probably contains NP. Okay. Okay. So, there are approximation algorithms for this, and the next step is where we find open problems are okay. So, terrain guarding. So, when the polygon that we want to guard is a terrain, that problem was shown to be NP complete by King and Krohn 2010. If it is orthogonal in addition to being a terrain, then also it is NP complete. It was shown by Bonnet and Giannopoulos, SOCG 2018. Okay. Ashok et al. In 2017 parameterized the terrain guarding problem by the number of reflex vertices in the terrain. So, this is not what they usually do. They want to parameterize in terms of the output, right. So, the number of guards needed should be the parameter usually, but reflex vertices, the number of reflex vertices, as you can see here, it can be huge, right. So, what we want to see is whether this problem can be parameterized by the output size, or is it W1 hard. Yeah. So, analogous problems for guarding orthogonal terrains and weak visibility polygons are also open, if you can have a good parameter. Okay. So, these are the open problems for art galleries. Okay. So, now we know what guard means. Yes. So, we will use this concept soon. So, there are two things that we will combine. So, one is guarding, two is coloring. Guarding, we have seen the types of problems that occur. So, a proper vertex coloring of a graph is an assignment of labels or colors to the vertices of the graph, so that no two adjacent vertices have the same colors. And okay. So, the k coloring problem is to decide if the graph can be colored with k colors for any given value of k. Okay. And so, the k coloring problem was actually open for since 1992, like it was the only optimization problem open for polygon visibility graphs. This we have solved last year. Yes, we have shown that like 4 coloring problem can be solved for polygon visibility graphs in polynomial time, and the 5 coloring becomes hard for simple polygons, and 4 coloring itself is hard for polygon with holes. Okay. So, this is normal coloring. Another version of coloring which has become very popular combines these two. It is called conflict free coloring. So, let us see what this means. Okay. So, consider a robot that navigates through a polygon and uses different types of landmarks for orientation. Okay. So, the robot is somewhere in the polygon and it wants to go to the other side, and at like each vertex should act as a landmark, seeing which the robot will turn itself in the right direction. Okay. And how many types of such landmarks are necessary such that the robot sees always at least one landmark and no 2 landmarks of the same type. So, the first version, so there are 2 versions of this again. Suppose the robot is here and I wanted to see all unique landmarks. Yes. So, as you must have guessed, the landmarks are basically the vertices and they are distinguished by the colors. Okay. So, if the robot is here and it wants to see all unique landmarks, this means how many colors are there? 1, 2, 3, 4, 5, 6, 7, 8. At least 8 different colors we will need to arrange for that kind of scenario.
Sorry to interrupt. I think they are not getting. See, suppose if you see you land in when flight lands there, then you see the lot of lights on the runway side. You know, the idea is that this pilot in the aircraft must know how to do the taxi, where to take the left turn, where to take the right turn. So each lights, earlier days, nowadays mobile is used, indicates whether to move straight and take a right turn. So if you see the red color, you say okay, move this way and then take a right turn. If the runway says green light, it says that. So these are the lights land, you see. So the pilot should not see 2 blue colors. 2 landmarks with the blue colors, 2 landmarks, so they should see unique different colors, so that they know what to do on the runway. So the landmarks must be unique. So at any point on the path, pilot must not see 2 landmarks of the same color. Because then it will continue to it says this way, it says this. So every color indicates some definite path to follow. So that this is the version which is talking about. So there will be no conflict in coloring.
There is immediate color that he sees.
Yeah, you can change, you can see different colors at different points.
Yeah.
But at any given time, you should not see two red colors or two blue colors. All colors should be distinct. So that the instruction it follows on the runway is clearly this. So this is one of the examples. Of this. That is, there are two versions of it. That's what you are talking.
So the version that you talked about, where all colors must be unique. So all colors unique. All colors.
Or colors of the landmark.
Yes, of landmark. Unique.
Unique from the viewing point.
Yes. So
From the viewing point. Viewing point can be anywhere in the polygon.
let's say the robot. Yeah.
The robot.
Unique from the robot.
Robot's current position.
Yes. So that is obvious.
The position changes.
Yeah. Unique from the robot. This is called strong conflict free coloring. Okay. But then you can see that this requires lots of colors, right? Okay. And you said about the airplane and airport, that analogy. There's another scenario.
So can you quickly color a few of the vertices that you have conflict?
Okay, so 8.
Assuming that the point
Yeah.
which you have drawn is actually replaceable.
Yes. So see, actually the number of colors needed will be more than 8, because if the robot is here, we need 8, right? The robot can be somewhere here. Yes. So it can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lots. Okay. So this requires a lot of color. Second thing is, second scenario is,
The color should depend on a particular position, or for assuming all the positions we are
all positions. Yes. Yes. There should be absolutely, there should, yeah. So there should be absolutely no point in the polygon which sees like repeated colors. Okay.
Maximum of all those deviations. For a particular viewing point, you have to minimize the number of colors. Definitely, yes. And for all viewing points, you have to take the maximum.
What is the issue?
From a given point, the vertices that are seen all have to have unique colors. There's nothing like maximum unique. You have to color
I'm taking all those the maximum. So what I was saying is,
if you take the maximum, then the coloring may not be achieved. You may need more than the maximum.
For instance,
Is like the if number, but what
for instance, if every vertex takes a
Suppose from one point, you see only 4 vertices.
So what is the question?
Another point it is 8.
Yes.
Then you have to take that 8.
No, but what I'm saying,
no, you need minimum 8.
Yes, that is true. That is true. That is true. Okay. Yes. Yes.
Understanding is clear, but
Yep.
Minimum you need. That's what he
Give a small example. 7 vertex.
No, this is
This is too long.
this is too long.
Reduce it. Make it
Okay. So say
one vertex.
yes. So what is the number of colors required for this strong conflict free coloring?
Hey, what are the number of colors? Answer.
6. 6. Okay. So 1, 2, 3, 4, 5, 6, and 2. Yeah. Yeah, 2 or 1, both can be.
2 cannot be conflict.
No, because if we want 2 can conflict. So this will be 1. Yes. Yeah, and wait, there's something here. So we need, yeah, so yeah, this is 5, right? So 6 colors for this.
Everybody convinced, because this is the scene, 2 weeks we will be talking and
Yes, yes.
examination have to be clear.
Yep.
Right? Otherwise, it will be another. So, there is no maximum, you just see sufficiency.
No, he's saying that there can be a very bad position in the polygon where the robot will see a lot of guards, and this he's referring to that as the maximum, and that will determine the number of colors that is needed, right? You are saying that there is a very bad position in the polygon where the robot will sit and see a lot of vertices, the maximum, right? And you are saying that will determine the number of colors. Yeah, that is actually correct.
No, suppose there is a point which sees all the vertices. That all vertices,
On the n is the number of.
Then n, of course, we cannot do better than n.
No, but what my question is,
Mhm.
suppose, so you vary the point. Okay?
Yeah,
At some point you are looking at 10 different
right,
vertices,
right.
but that is the maximum.
Mhm.
If you vary the robot, the position of the robot.
This is all we
So
I'm
the,
saying, still it's possible, or it is at least not obvious why the whole thing can be colored with 10 colors. Maybe
right, yes, yes.
It may take more than 10 colors.
Yeah, there's, because see, what you said is a local property. If that determined everything, then it would have been polynomial time. Okay, this is not, this is NP complete. Okay,
because then you can again do this triangulation.
yes,
Each triangle you can put a viewer,
right,
and I think you
yeah, yes, correct. Okay.
can again put the triangulation. But to make it triangle, robot,
So that's a good point actually.
That 10 colors is not sufficient. It may take 12 colors.
So it will tell you, it will give you a lower bound on that particular polygon. So yeah, I know, yeah, but so let me define the problems at least. Right, okay. So this is only one type of conflict free coloring, and this requires a lot of colors. So consider the scenario in which you have told the robot, okay, you have told the robot that wherever you are, look for one unique color and orient yourself according to that. Okay. Alternatively, so the vertices are transmitters, colors are frequencies, and all the robot wants is one unique frequencies from where it can get instruction. Yes, because if there is like more than one for each frequency, then there will be interference. Okay. So I will give the example. Yes. So what happens for this? For this point, under our previous notion, strong conflict free coloring, we were requiring 8. Yes. With our new notion, which requires only one unique color, we just need color 1, let everything else be color 2. Yes. I will give another clearer example why this is so much superior. So this is called weak conflict free coloring.
I think definition is clear.
Yes, I will give examples, it's not complete.
Because it's something new to many people, so
Yes, and there is,
very slow.
and the difference is one color of a landmark must be unique. So let's see an example where this is pronounced very nicely.
Okay, you explain. Let me say one more word in inclusion.
Okay.
Suppose you have a mobile, you are moving with your mobile, right? It has lot of towers which you can communicate through. So at any given point, you need one correct frequency to communicate. That means at any given point, there will be two colors correspond to frequency.
So so consider this type of comb polygon. There are spikes. Okay, the spikes are such that so take the first spike and look at its apex. It can see somewhere here, which say the k spike apex can also see. Yes, there are k spikes.
That means if a tumor is there,
It can see the spike apices of both.
among all of them,
Yeah, everything in between also. Yeah,
but not the other one.
right. And so there are k spikes. Suppose that there are a total of these groups of k spikes. There are k of them continuous. Yes, so say k groups of k spikes. So now the question is, we want to do a strong conflict free coloring of this polygon. How many colors do we require? Yes, k or k plus 1. Yes, of course. So all of these k actually, all of these need unique colors 1, 2, 3, 4, 5. Why? Because if any of these have same color, yes, the guards guarding the spikes, if any of them have the same color, then there will be some conflict below, right? Okay. Or you could say, why do I need to put? Yeah. Why do I need to put guards here? I can put a. I mean, I don't need guards here. I can put a guard here, right? If I do that for every group of k spikes, then the guards sitting here will also need unique colors. So either I put k unique colors here, or I have to put k unique colors below. Yes. So for strong conflict free coloring, this needs k colors. So for n vertices, it is something like omega root n, right, are needed. Root n colors are needed for this. But if we consider the weak conflict free coloring notion, say one color of a landmark must be unique, then how many do we need? So now the robot must see just only like one unique color, that will do. Two, of course, yes. So put color 1 here on the top. Yes, everything is color 1 on the top. And put your second guard over here. That anywhere. 2 are enough.
That means every viewpoint we see many one, but we see only one of that is two. So it's a conflict free color.
Yes. But then the question is, for this polygon I have done with 2 colors. Yes. What about a general polygon? Is there some polygon that needs more colors, or can we say that maybe not with 2? There is some upper bound for polygons in general for weak visibility, weak conflict free coloring. Yes. So I was thinking of going ahead with your proof. It's that one.
No, now I think your time is over.
But yeah, so now we know that. Now we know at least what the problems mean. Yes. So maybe next time.
If it does not extend your time, you have to stop.
So you can take a break, have tea and come.
Yeah, of course. Yes, yes, sure. Yeah, yeah.